Hello, everyone. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Felipe Zurita, we will be your guides in this virtual trip to La Silla Observatory. Just a little bit about me. I am one of the tourist guides of Paraná Observatory for more than 10 years. So I have some experience in astronomy outreach and education for many years, and I will be in charge of presenting this virtual experience. But as I told you before, I am not alone. I am with the producer Felipe. Who are you, Felipe?
I'm fine. Hello, Farid. Hello, everyone. I'm Felipe Zurita. Today, I will be the producer of this online tour, and I'm excited to help bring this experience for you. Today is La Silla Observatory in English, and feel free to leave your questions about astronomy or about what we are showing today in the comment box in the leave your comments or greetings. And Farid, today will show the La Silla Observatory. Every Saturday have a virtual tour to Paranal or to La Silla. So thank you for seeing us today, and come on, Farid.
Yeah, thank you very much, Felipe. So yeah, ESO wants to be with you during this virtual experience and bring astronomy directly to your home or wherever you are. So we will have some time in the future to answer some questions. So you can leave your comments or questions in the um, Facebook or uh, YouTube, and we are going to answer all your questions later. Okay, so we are going to start immediately. And the first thing I want to do is to talk a little bit about organization. I want to talk a little bit about the European Southern Observatory. So ESO is an intergovernmental organization. It is composed of 16 member states. Its headquarters are located in Germany. And also Australia has joined ESO, in this case as an strategic partner. And Chile is the host state and is the home of all ESO observatories. So from the 60s, and with those objectives in mind, ESO did choose one of the best places on the planet to perform astronomical observations, the Atacama Desert in Chile. So around that time, Chile had started an exploration campaign of several sites in the Atacama Desert to attract international observatories such as ESO to our country. So Chile offered its territory, and ESO did choose the areas that seems best. So the mission of ESO is basically to design, to build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Now, in the next picture, you can see the three observing sites of ESO in Chile. So first, we have the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. So the VLT is at this time, at the present day, the most advanced ground-based observatory on the planet. In the future, and next to Paranal, only 20 kilometers away, we will have the Extremely Large Telescope, or ELT. This will be the biggest visible light telescope on Earth. And near there, we will also have the CTA, the Cherenkov Telescope Array. This is an array of telescopes to be focused on gamma rays. We also have Chajnantor. Chajnantor is the site of the ALMA radio telescope. In this case, ESO is part of this radio astronomy observatory alongside other international partners. And last, we have the site of our visit, our current virtual experience, La Silla Observatory. This was the first observatory of ESO in Chile, and this one is located in the Coquimbo region, in the north of the country, around 2,400 meters above sea level. So we are going to visit that place during the next hour. So now we are going to start this virtual trip, and we will have our planet in the in this animation. So we need to start this journey in Europe because ESO is an European organization. And in this map, outlined in white, we can see the different states. I mean the ESO states. Okay? And Chile, in this case, is participating as the host state and is the home of all ESO observatories. So, in order to know more about this observatory, we are going to travel to the Andes Mountains in the north of Chile. Now, during this journey, we are, uh, let's say, flying over the Atlantic Ocean. I can tell you a little bit more about the mission of ESO. So, basically, the mission of ESO, the work of ESO, is basically to imagine what type of instruments we need to study the universe. So, it's in charge of uh, designing the pieces, to build the telescopes, and to operate the telescopes, to receive some observation requests from different astronomers. And in this way, we can incentivize the promotion and cooperation in the astronomy field. Now we are almost arriving, and you can see several mountains there, but you can see that this mountain, La Silla, is well, the name La Silla or the chair is because it reminds you of a horse saddle. Okay, so that's why we have this name La Silla. Okay, it's because of a horse saddle. Now in this animation, well, this is actually like a drone view. We can see the different telescopes located in La Silla. La Silla is located at 2,400 meters above sea level. This observatory was inaugurated in 1969, and right now we have 10 telescopes operating there, and two of them are operated directly by ESO. You can see the names of each telescope in this flyover, and we are approaching to the first and biggest telescope in La Silla Observatory. I mean the 3.6-meter telescope of ESO. Now, in this case, it's important to mention that some of the telescopes in this observatory are not in operation anymore because this is a very old observatory. But right now, we still can operate a few of them. But in most cases, the telescopes in operation are operated by other organizations remotely. Okay, I mean organizations belonging to ESO member states. So essentially, the two telescopes operated by ESO are the 3.6-meter telescope here and the NTT, the New Technology Telescope here. So we are going to visit both telescopes today, and we are going to start with this one, the 3.6-meter telescope, because this was the first telescope inaugurated in this observatory. Okay, we're going to access right now, so I can show you what happens here. Okay, so we are inside of the 3.6-meter telescope, or 360. This is a nickname for this telescope. And you can see that this is a very big telescope, and the enclosure The dome, of course, is very big. You can see here. You need to understand that the name of this telescope, 3.6 meter, is a reference to the diameter of the main mirror, of the primary mirror. So essentially, when this telescope was in operations in the 70s, this telescope was among the biggest telescopes on Earth. And right now, we have a very special instrument in this telescope. It's essentially an exoplanet hunter. The name of this instrument is HARPS, and this is a highly specialized instrument. And every night we are trying to look for exoplanets. I mean, planets orbiting other stars outside our solar system. So, as I told you before, this place is very big, of course. It's a giant telescope, and from the first floor until the dome, we have 25 meters. And all the telescope structure is about a 7-story building. Okay, so this is the approximate height of this telescope. So everything looks small if you compare with a telescope. So for example, we have a person here, right here. So I will do a close up so you can see this person here. So you can have an idea of how big is the telescope. You see, if we compare with the person here. So in this case, well, I am going to open a picture because I want to explain a little bit about the composition of this telescope. Because we have different components and different structures in this big telescope. So we have some important things that we can distinguish in this picture to the right. First, in dark blue, right here, we have the structure supporting the telescope. This is the mounting of the telescope. Okay, so this mounting works as a very big arm holding the telescope and containing several systems, for example, for the energy, for the electricity, and on top of this arm, of this mounting, and parallel to the Earth's rotation axis, the telescope is moving to follow the objects in the sky during the observation. Okay, I think we have a short video to show you how the telescope is moving to have an idea. Can you please put the video, Felipe?
Sure, sure.
Thank you.
This is the movement of the 3.6 telescope is too slowly and loudly.
Thank you, Felipe. So yeah, so this is how the telescope is moving. As you can see, it's impressive. See, this is what happens when the telescope is trying to follow. I mean, um, to change the position and to locate another object in the sky. Okay, so if we continue with the picture here, and in light blue, right here, all of this is the telescope's body. Okay, so in this structure, we have the main mirror, the primary mirror of 3.6 meters or 360 centimeters. And also we have the secondary mirror. Now, where is the main mirror, the primary mirror? Well, the primary mirror is not visible here because it's covered by its protection system, this black structure. This is a system of tabs, so we can open and close those tabs to protect the mirror from dust or moisture when the telescope is rusting, I mean when it's not observing. Now, in the tubular structure here, in this area, we have the secondary mirror. So the secondary mirror will collect the light from the main mirror. So the light will be reflected again, and this light is going to pass through this hole in the center. because the light eventually will reach the main instrument. Now, the main mirror, as you can see, there is a hole in the center, okay, and essentially, as I told you before, the light is going to reach the main instrument. In this case, is going to reach the harp's instrument. Okay, so when you have the telescope observing at night, the light from the stars is going to impact first in the primary mirror. The primary mirror is concave. Is like a spoon. Okay, so when the light is going to the primary mirror, is concentrated, is reflected to the secondary mirror, and is reflected again. This is what happens. Okay, so essentially the light will reach the main instrument, and this instrument, the harp's instrument, is not visible here because is completely isolated in another room, in another floor of this building. So that's why it's not visible in this picture. Now, the 360 started operations in 1977, and of course, it was a big challenge for engineering, and it represented the big mission of ESO as an organization. So, European astronomy was just starting to collect and gathering, expertise from different countries to build an optical telescope in the 4-meter category. So, at that time, in the 70s, it was the biggest and most advanced category for an optical telescope. Okay. Now, why it was necessary a telescope of this diameter, of this size? Well, in astronomy, we analyze our objects through its light. So the more light we collect, the more we can learn. Now, in this case, if we have a bigger mirror, we have more light to analyze, and we can know more details about the different objects. So we will be able to observe fainter objects and to distinguish smaller details. Now, a mirror for astronomy is not like a typical mirror. Okay, as I told you before, it's a concave mirror. It's like a spoon. Now, the shape and the surface has to be perfect in the level of fractions of millimeters, or let's say tenths of millimeters. Now, to achieve this in the 70s, it was necessary to build a mirror very special, and this mirror is extremely thick. The thickness of this mirror is about 53 centimeters, but this implies that this mirror is extremely heavy. The mirror, the weight of this mirror is 11 tons. This is equivalent to 2 African elephants. And if we want to build bigger telescopes, we need to find different solutions. So, what was the next step? We are going to explore the answer in the NTT, in the New Technology Telescope. Okay, so this is basically the explanation about the 3.6-meter telescope. So I hope you enjoy this giant structure here. But now we need to go outside because we need to continue, and we need to continue with the NTT, the New Technology Telescope that is located right here. But before talking about the NTT, I don't know, Felipe, if we have any question to answer
Uh,
about
we
the
don't
observatory.
we don't have any question until now, but for people see us, remember you can leave your questions, reading about the astronomy, about the virtual tour, about the 3.6 telescope or NTT telescope later. Remember that this is a virtual tour that can I that we can teach you about astronomy, how works the the telescope work. So remember, leave your question or reading or annotation whenever you want to, and we try to answer your question about anything you know to know about the astronomy or galaxy or a telescope. So we don't have any further.
It's okay. It's okay. So I hope we can answer some questions later. So please remember to leave any questions about the observatory or astronomy in general, and we will try to answer that later. And by the way, something important to mention is that La Silla is accepting public visits. Okay, so we have a public visits program for La Silla and Paranal. So in this case, maybe Felipe, you are more familiar with with La
Yes.
Silla's visit program. So can you please tell me quickly what are the main uh, times to visit La Silla?
um, La Silla, Paranal too. In La Silla in particular, you can visit every Saturday or Sunday in winter season. You can visit La Silla every Saturday or Sunday. In this time, in summer season, you can only visit in Saturday in two periods, in 10 to 10 and 1 o'clock, and the second visit in in the afternoon is to 2 o'clock at, I remember, to 5 o'clock. So you can visit in two periods in the same Saturday day, and any Saturday of the years or Sunday in winter season, and only you need to reserve in the ESO page, ESO.org. You can take
Okay.
a place in the visit of the La Silla.
Thank you very much, Felipe. And also important to mention that when you say the winter season, is winter in the southern hemisphere,
Yeah,
because yeah, for our virtual visitors from Europe, from USA, winter in the southern hemisphere is um, May, June, July. Summer is December, January, February. So this is important to mention.
mhm.
Yeah, because uh, the available time to visit the observatory, it depends on the season. Yeah, but this the season in the southern hemisphere. Okay, so we are going to continue now. So we finish now with the 360, and before going inside of the NTT, the New Technology Telescope, I want to highlight the main differences with the domes. So you need to understand that both telescopes have a mirror that is almost exactly the same size, the same diameter. Okay. Now the NTT, the New Technology Telescope, was inaugurated in 1989, and the dome is very small and compact. It's an octagon design with a system of flaps. So this represented at that time an evolutionary leap in the construction of telescopes, because this enable well this allowed to host the instruments in smaller lightweight structures, and also much more efficient in terms of the circulation of the air in the interior. So basically the domes like the 3.6-meter telescope, now you can consider this kind of dome or classical dome a little bit more obsolete. Okay, so in this case, if we come back to the NTT, these kind of flaps in this kind of dome are very important and useful because the air can, uh, let's say, can flow and with no obstacles, and this can reduce the possibility of turbulence, and therefore we can preserve the sharpness of the pictures. Okay. Okay, so now we are going to access the entity. And if you remember the structure of the 3.6-meter telescope, well, you know the giant dome and the yeah, and that everything looks very small inside, right? So in this case, um, the building of the entity is very different. You can see the flaps there, and you can see the telescope here, but you can see that everything looks more compact, okay? Because in this case, the building is like attached to the telescope. So when the telescope is rotating, everything is rotating. All this dome is rotating. So it's like the rotation of the telescope involves a rotation of all the building. And if you look at this door, you can have an idea of the size of a person, you know. So in this case, if we have a person here, well, the difference is not it's not too big if we compare with the 3.6-meter telescope. So um, in this case, also if we analyze this telescope, um, the mounting of this telescope is totally different. Okay, so it's a different design, is attached to the telescope, and when we rotate the telescope, remember, all the building is rotating. But when the telescope is tilted, well, of course, only the telescope will be tilted. Okay? I will change the view to show you the opposite um, perspective, and you can see that everything looks so different if we compare with the 3.6-meter telescope. Now, in this case, if we focus on the main mirror there, this is the mirror, you can see that the mirror is this structure here, and um, as I told you before, this mirror is very, very similar to the mirror in the 3.6-meter telescope, because this one is specifically 3.58 meters. Okay, so it's almost 3.6 meters. And in this case, this mirror is 24 centimeters thickness, and is well, let's say it's not so heavy like the 3.6-meter telescope. I mean mirror. In this case, the weight of this mirror is 6 tons. This is the equivalent of one African elephant. So this is essentially the mirror of the NTT, the New Technology Telescope, and this mirror is also concave. It's like a spoon. Okay, so this is the primary mirror. This is the secondary mirror. Okay, so in this case, the design of the mirrors is more or less similar, but you need to understand that because this mirror is concave, because, well, I am talking about mirrors in general for a professional observatory, because the mirrors are concave. We need to understand that these kind of mirrors are heavy in general. So when the mirror is tilted, okay, when we need to put the telescope inclinated, the mirror, because it's so heavy, can suffer some distortions, deformations, just because of gravity. So we need to do something to preserve the concave shape of the mirror all the time. I mean, we need to avoid any distortion, um, any kind of deformation because of gravity or physics. So in this case, in the new technology telescope, uh, we are including a very important, very interesting technology. So you can see that underneath we have this structure. There is something below the mirror. There are some actuators. This is a kind of piston. We have 75 actuators underneath, and the actuators are essentially doing a small pressure, are are basically providing a small pressure. I mean, it's going to push up and down, because in this way we can compensate any distortion on the concave mirror. So essentially the shape of the mirror is always the same. We are preserving the same concave shape to preserve the same quality of the final picture. Okay, so that's why we are including the actuators underneath. Now, this technology is called active optics, because we are doing a kind of active action on the mirror. And this technology was developed by ESO, and the new technology telescope was the first telescope to test this technology. So now this technology, active optics, is implemented in the very large telescope and any modern telescope, and it will be also included in the upcoming extremely large telescope. So active optics is a very important kind of technology um, regarding the mirror. Okay. So essentially, at the present day, we are working with different kinds of mirrors. For example, Paranal, they have mirrors of 8.2 meters in diameter. So it's very important to apply the active optics technology, because, for example, the mirrors of Paranal, 8.2 meters, are heavier than the mirrors in the NTT or 30.6 meters. So it's very, very important, and that's why we are applying the active optics technology in modern telescopes. Okay, so this is essentially what happens here, and now maybe you are asking yourself, well, where are the scientists? Where are the astronomers? Because in the 3.6 meter telescope and in the NTT, we don't see any, let's say, office or control office, I mean, the control room. That's because the astronomers are not physically here. They are not physically in the NTT, they are not physically in the 3.6 meter telescope, because they are working in another location. They are working from a control room, but the control room is in another place. I mean, it is in the observatory, but not here. It's in a separate location, because we are doing a remote control of the telescopes. And we have a short time lapse to show you what happens in a typical night in La Silla. This is the control room. And you can see that we have a few people working here in two workstations. So one workstation belongs to the NTT, the station to the left, and the workstation to the right belongs to the 3.6 meter telescope. So you can see that we have several computers for different purposes, and we have a few scientists working there. We don't need a lot of people. We need probably one telescope operator, maybe an astronomer, and they are working all night. They are working, they are supervising all the observations. And of course, this is a very comfortable location, so they can work from there comfortably all night. So this is basically what happens in La Silla control room, and this is to well, basically to provide some kind of practical view of what happens during in the night. Now we are going to move move on, and we are going to share something very interesting. We are going to share with you some of the main scientific milestones from all ESO sites. But before doing that, I don't know, Felipe, if we have any question.
We have an interest question, a one question, and that's a when you are observing, which part of the process feels most different from how astronomy is usually presented to public? The most different part of the astronomy. In
Well,
particular, for me, I
mhm.
think the process, image process, is the most different part for me.
Yeah, yeah, yeah. We can, for example, talk about that. When you look at the beautiful pictures, some beautiful picture of a galaxy, of a nebula, whatever. This is not exactly a picture like the picture you can take with your cell phone.
Hmm.
So in astronomy, in professional astronomy, you need to usually take several pictures, long exposure pictures, and usually they are black and white, and you need to combine pictures taken with different filters. So you need to do some kind of post processing, and you need to essentially combine different filters into one single picture to create something like a color picture. And depending on what you want to um, let's say highlight in the
Mhm.
final picture, maybe you need to emphasize um, some chemical elements present in the picture. So for example, in a nebula, maybe some parts of the nebula will have more oxygen, more helium, more nitrogen, etc. So maybe you can assign some false color or something like that. So essentially, in the final pictures, you can see it's not exactly what the astronomer is looking at the telescope. It's the result of a more complex post-processing procedure.
That's right. Is the most complex, and we need to be careful of work in the image. And this is the part I think is the most different in astronomy. But this is the only question I have. So let's start in the top 10, right?
Yeah, thank you. We are going to present the top 10.
So let's start.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, we are going to share with you an extra result, something like a bonus track. So we are going to show this quickly. Is something that happened a few years ago. It's about the black hole. Yeah, this one. Thank you. This was basically that a team of astronomers was able to capture the first picture of a black hole. In this case, the Event Horizon Telescope, or EHT, an array of 8 ground-based telescopes distributed on the planet, thanks to an international collaboration, was able to get the first direct visual evidence of a supermassive black hole. In this case, the picture will reveal the black hole in the center of Messier 87. This is a massive galaxy in the nearby Virgo galaxy cluster. This black hole is at 55 million light years from Earth and with a mass of 6,500 million times the mass of our Sun. Okay, so now we are going to continue with something very interesting, because in this picture, we can see La Silla at night. So we are going to share with you some interesting objects of the night sky visible from the southern hemisphere, and this is just an example of what is the typical night sky from the Atacama Desert. So we are going to show you first a very popular constellation just next to the NTT. I mean, if you look at this, this is the New Technology Telescope, and next to it, we have a constellation very near the horizon. This constellation is Orion. This is very popular, of course, and it represents a hunter, okay, with those three stars somewhat aligned, representing Orion's belt. Okay, so this is what happens here. Orion is visible from the northern hemisphere and the southern hemisphere, so everyone can observe Orion. And there's something very interesting in this constellation because next to the three stars here representing Orion's belt, we have this object. This object is the Great Orion's Nebula. So this is basically a star forming region. So new stars are forming there, and this object is very interesting because it's very big and it's bright. So you can observe this object even with your naked eye. I mean, you can observe this object like something like spot in the sky if you have a dark night. And of course, you can observe the Orion's Nebula with a small telescope or even binoculars. So it's very, very interesting for amateur astronomers. Now, if we continue moving up, we will eventually um, reach this star. This star is the brightest star in the sky. Its name is Sirius. Sirius is part of a constellation called Canis Major. Canis Major in the mythology is one of the hunting dogs of Orion. So essentially, the constellation of the brightest star in the sky is connected in the mythology to Orion. Now, if you look at this area of the sky carefully, next to Orion, next to Sirius, you can see that this area has more concentration of stars. You see, we have a lot of stars here, we have a lot of stars here, but this area has a bigger concentration. This is because this is one of the arms of the Milky Way. So we can see that the Milky Way is our galaxy, right? So our sun is part of the Milky Way, of course. So our galaxy is essentially a immense flattened disk with an spiral shape, but we look at the Milky Way like bright band in the sky. Okay, just for a matter of perspective. So you can see beautiful features here, dark clouds, bright nebulas. You see, all of this is possible to observe from the southern hemisphere. Now, I am going to change the view now because I want to show you two interesting features here. I want to show you those spots in the dark sky. So what is this? In the southern hemisphere, we are lucky to see the Magellanic Clouds. These are actually galaxies. They are irregular galaxies. They are satellite galaxies of the Milky Way, so they are orbiting our Milky Way, and they are only visible from the southern hemisphere. But why we call those objects the Magellanic Clouds? Because the name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So for him, those objects just look like clouds because in the 16th century, no one was aware what a galaxy is. So for him, this looks like clouds. So that's why we call them the Large Magellanic Cloud and the Small Magellanic Cloud. Okay? There is something else. We have the smallest constellation in the sky, the Southern Cross. This is also only visible from the southern hemisphere. It's here, it's tilted in this picture. So this is, as I told you before, the smallest constellation in the sky. And the Southern Cross is very interesting because, in the southern hemisphere, if we want to point to the south celestial pole, I mean the projection of the south geographical pole in the sky, we don't have any bright star here. This is not like the northern hemisphere, because in the northern hemisphere, northern observers have Polaris. So Polaris is a very bright star that is very close to the North Celestial Pole. But in the southern hemisphere, we don't have any bright star here. So a technique to find the South Celestial Pole is to project the longer stick of the Southern Cross about 4 times and a half. So if I do this, I will do it is 1, 2, 3, 4 and a half, more or less like here, we have the South Celestial Pole. So essentially, if you take a long exposure astrophotography toward this direction, you will see circles, okay, like concentric circles here, because this is a projection of the geographical South Pole. And also, you can get the same thing. You can get the South Celestial Pole if you try to imagine a triangle using the South Celestial Pole as one of the corners, and you try to to use the Magellanic Clouds as the other corners. So this is what happens here. Okay, so and just to finish this explanation, I am going to come back to the 3.6 meter telescope, and you have a beautiful view of the center of the Milky Way rising behind the 3.6 meter telescope. This area is very, very beautiful because you have a lot of dark clouds here. You have the Scorpius constellation, and in the southern hemisphere, this is especially interesting because in the southern hemisphere, in winter months, I mean in May, June, July, you can see all the Milky Way about you. And this is a difference if you compare with the northern hemisphere, because in the northern hemisphere, it's not possible to observe all the Milky Way. You can see something like the 75% or something like that. But in the southern hemisphere, in winter months, you can see all the Milky Way. So that's why it's a very popular destination for astrophotographers that likes to come to the Atacama Desert to take pictures of the Milky Way. Now, we are almost approaching the end of this virtual experience. I am in this picture, I am in the platform of the 3.6 meter telescope, and we can see the other telescopes in the horizon there. I am going to move to the road connecting all the telescopes in La Silla. You can see this is a road. So if for any reason we need to access the telescopes, the astronomers, the scientists, they can use this road. And essentially all this road will connect everything with hotel, with La Silla Hotel. So in La Silla, we have some kind of hotel for the staff. So in this place, we have a restaurant, we have the bedrooms for the people working in the observatory, so they can enjoy a peaceful and very beautiful place to rest. And this person here is the astrophotographer who was in charge of everything, of all the pictures. And as I told you before, from the southern hemisphere, you can see the full Milky Way in winter months. I mean, May, June, July. So, for example, this picture, as you can see here, will show you all the Milky Way in the sky. So you can see the center of the Milky Way in the zenith, and you can see this beautiful, beautiful view that is only possible from places like the Atacama Desert. And that's why we have several observatories in the north of Chile, including the ESO telescopes. Okay, I am going to finish here. So I don't know, Felipe, if we have one last question, because this will be almost the end of the virtual experience.
Just appear a question is what is something about operating La Silla day to day that surprised you when you first start working there, and that you still think most astronomers outside ESO don't really appreciate? And another astronomers, I don't think another astronomer don't really appreciate, because La Silla, the reason is a old observatory, have a beautiful views, have a nice place of view of Atacama Desert. Farid show you the night sky and La Silla. So personal, I worked in La Silla about 10 years, but the first time I surprised in this place in La Silla is when entry the 3.6 telescope. 3.6 seems giant, but inside is more giant than you can look. And this is the last question I have. Farid, you visit La Silla too?
Yes, yes. And well, from my perspective, I think, well, many modern astronomers, they can work from a desk, they can
Mm,
work from a computer in an office, and of course it's totally fine. But when you visit La Silla, when you understand how the classic astronomy was performed, you understand. For example, I was lucky to spend a night in the Danish telescope, and
mm,
other old telescopes, and you are in charge of operating different things. Not,
mhm,
I mean, you can control the focus, you can control the opening of the dome. In some telescopes, you can even put the liquid nitrogen. So when you experience an observatory like La Silla, it's like you have this very amazing perspective of how astronomy in the 70s or in the 60s was able to achieve so many discoveries and so many beautiful and impressive things, in a more, like, say, manual way. It's difficult to explain, but maybe this is something that probably the modern astronomers, it's not that they don't appreciate that, it's just that they don't, maybe they didn't experience that. So, so I think this is some of the beautiful things you can experience in a place like La Silla, because you can understand how difficult was to work with limited resources, with limited technology. So that's my opinion about the beautiful heritage of La Silla as an observatory.
it's beautiful answer too.
Yeah.
And it's it's just in time today. And thank you for the questions. It's time to over this virtual tour. Remember, we have every Saturday. This is the last Saturday of the years. the last virtual tour of the years, but every Saturday I have a visit to Paranal and La Silla between one Saturday La Silla, one Saturday Paranal in English and in Spanish. So this is in English. The next week probably is in Spanish. So I today I say goodbye and I give you the words for it.
Yeah, well, from my side, thank you very much for attending this virtual tour. All these visits, information, pictures, and etc. is available on the ESO website. So I hope you enjoy it. And on behalf of ESO, we say thank you very much for your presence and Happy New Year.
And happy New Year too. Bye bye.